Okay, so now it's section 1.5, sum of a series. Before we start going through the complex numbers sum of a series, we're going to remind ourselves of geometric progression formulae, the sum of the series of geometric progression. So obviously geometric progression, you have got the sum of the terms where you are multiplying the previous term by the common ratio to get to the next term. So here A is the first term, R is the common ratio, and you are going to sum n such term. This actually here is the nth term. So here's the formula. I prefer this form. You may have learned it as A in brackets R to the power of n minus 1 over R minus 1. I prefer to use this version though. Then you also remember from the pure year 2 chapter, sum to infinity of geometric series is simply A over 1 minus R, provided the ratio is, the common ratio is between minus 1 and 1. If it's between minus 1 and 1, then this series is convergent. Okay. Before we start example 13, I'll show you a useful trick that we'll do a couple of times in the next two examples. So it enables us to use these two identities. So here we go. So the thing to do is, first of all, to note is it works with a complex number plus or minus 1, or 1 minus plus or minus a complex number with a power. So the idea is to make this bracket into z with a power plus another z with a power, and those powers need to be equal in size, magnitude, but opposite signs. It's very, very simple. You've got to multiply the bracket by z with the power that makes this power into half of it, so clearly minus 1. So imagine multiplying it out. You are going to get z to the power of 2 multiplied by z to the power of minus 1. When you add the powers, you get z to the power of 1, and then 1 times z to the power of minus 1. And this one here, clearly it can be replaced with 2 cos theta. So over here, let's just think, what could we multiply this by? It's by half of whatever the z has as a power. So it's got to be a half, but with a minus. So when you then multiply it out, you get z to the power of 1 times z to the power of minus a half. And adding the powers will give you z to the power of a half minus 1 times z to the power of minus a half. Okay, so this one over here is going to be with a minus, so it's 2i, the second identity, sine, almost wrote cos, theta over 2. Okay, now you can have obviously the terms reversed, so over here still the same idea. Let's multiply it by z to the power of half of this power, but with a minus, so minus n over 2, and let's multiply it out. You're going to get z to the power of minus n over 2 minus z to the power of n times z to the power of minus n over 2. So adding 1 plus minus a half n gives you n over 2 as the power. So this one clearly, if you take the minus out, you have z to the power of n over 2 minus z to the power of minus n over 2, which gives you minus 2i sine n theta over 2. Now over here, you need to really be careful. These three work. This one, if you try and do the same trick, so you try to multiply it by z to the power of, let's choose half of that is 3 over 2 minus 3 over 2. You get 2 times z to the power of minus 3 over 2. Add z to the power of 3 times z to the power of minus 3 over 2. That gives you 3 over 2. You can't replace this expression with the identity. You've got 2 of these and you've got only 1 of these. So if you had 2 of each, that could work because you could factorize 2 out, but not of different amounts. So you cannot use the identity here.